says recording is pending. Go.
So today we're going to talk about the longest path problem and why it is NP hard. And so what the longest path problem is we need to find the longest simple path through any given graph. And a simple path is just one where we don't repeat any vertices. And then the length of a path is measured either by the number of edges that we go through if it's an unweighted graph, or the sum of all the weights of the edges in a weighted graph.
So when we were researching the difficulty of the longest path problem, we found that the difficulty varies based on different applications of the problem. In its standard form, we found it to be NP hard. And then if you were to reduce it to the decision version of the problem, which basically refers to solving for the existence of a given path with a given length, that difficulty is NP complete. However, when you actually take the problem and apply it to a directed acyclic graph, the difficulty reduces even further to linear time.
And so what we can do is we can take the longest path problem and we reduce it down to the Hamiltonian path problem. Because a Hamiltonian path is one that goes through every single node in a graph exactly one time. So it's not going to repeat itself. There aren't any cycles, but we do reach every single node. And if we think about the longest path would be one that reaches every single node. So it'd be a length of n-1 if it's an unweighted graph.
So then with the longest path problem being reduced to a Hamiltonian path problem, we reviewed a number of different algorithms that could be applied to come to a solution. And we actually went into the Bellman-Held-Karp algorithm, which uses dynamic programming in order to solve the problem. And in the worst case scenario, it came out to an O(n) squared 2 to the n time, which is significantly faster than the O(n) factorial brute force algorithm, but it's still very slow and complex.
And so in this slide, we're going to explain why it's a big O of n factorial if we just do a brute force. Because what we would do is we would check every single option in a graph and then compare those against which one is the longest. And so starting out, we have an option of n nodes to start from. And so, for example, let's start at this one. And then once we choose this, we have n-1 options. And so then we go here. And then from now we have an option of this one, this one, this one, this one, and this one. So n-2, and then we continue to get n factorial.
So that led us to really look into the Bellman-Held-Karp algorithm, which basically works by, with each vertex numbered 1 minus n. The algorithm basically creates a set of vertices. With each vertex v is found in S, it looks to see if there's a path that exists that covers each vertex found in S and it ends at V. And for every option of V and S, there exists a path for SV if and only if V has a neighbor Y such that a path exists for S minus VY, which is looked up from a previously stored dynamically programmed solution.
And then another option that we looked at for solving this problem was a variation of the Floyd-Warshall algorithm. And so what we do for it is we negate all the weights for the edges in the graph, so just multiply them by -1. And then we use Floyd-Warshall to find the shortest path between all the specific nodes. But once we have that table that the Floyd-Warshall algorithm gives us, we're going to just do a simple two-dimensional for loop to find the minimum there. And then once we negate that, that'll give us the cost of the longest path in the graph. The biggest drawback with this is it doesn't work if there are cycles in the graph. And that's really the most difficult part of this problem, is when there are cycles, that's what's going to give us an NP hard, or sorry, time complexity that is exponential. Because, for example, with the Floyd-Warshall program algorithm, if there is a negative loop, we're just going to keep taking that because that makes our path shorter and shorter. And so it's NP complete because of problems like this, where it's not just a simple graph.
And here are the references we used for our research. And thank you for your time.